In this problem, we're in a prison and we have n ID cards. There are m gates in this prison, and each gate only accepts a certain number of cards. And we just want to find the number of cards that let us pass through all the gates at once. Okay, so in the first line, we're given n and m, which is the number of cards and the number of gates. And then in the next m lines, we'll see which cards can go through each gate. So here, this is the first line after n and m, so this is gate 1. And in gate 1, it accepts cards number 1 all the way till 3, so 1, 2, and 3. And here, in gate 2 accepts cards 2, 3, and 4, right? So this is the lower bound and upper bound, and they're both inclusive. So over here we can see if we have card 1, we can go through here, but not here. So that doesn't work. If we have card 2, we can go through this gate, and it's the same for card 3. But if we have card 4, we can't go through the first gate. Right, so in this case, using card 2 and card 3, we can pass through all the gates. So yeah, we just want to count how many of the ID cards let us pass through all the gates at once. So at first we're given n and m. Then in the next m line, we're given a lower bound and an upper bound. So the key thing to notice is all we have to find is the largest left value and the smallest right value, because that would be a subset of keys that can pass through all the gates, right? So here the largest left value would be 2 and the smallest right value would be 3. So as we know, in the subset which starts at 2 and ends at 3, so that only contains the cards 2 and 3, and our answer is 2. Using that same logic, let's look here, right? Biggest value is 6, smallest value is 6, so only the card 6 can go through all the gates, which is true, so the answer is 1. Over here, since there's only one gate, any of the IDs that are in this range will work, so therefore there'll be 100,000. Yeah, so that's all we have to do. So we can just have, we want the biggest L, which is initially at 0, and the smallest R, which is initially at infinity, right? So then we can say big L equals max of the new value we get and the previous biggest L we have seen, and using the same logic, the small r is going to be the minimum of our current smallest r we've seen so far and the current r we just got, and then we just output the max of small r minus big L plus 1 and 0. I think this should work. Let's check. Okay, 2. Whoops. 1 and 100,000. Yeah. Okay, so let's say we have an edge case, right? So let's say we have 3 gates with 3 numbers, right? And then we have, this is 1 1 2 2 3 3. So the first gate accepts only card 1, second gate only accepts card 2, and the third gate only accepts card 3. So then it's obvious that no one card can go through all 3 gates at once, right? And then if we find our big L and our small r, our big L is going to be 3 and our small r is going to be 1, right? Because the smallest r is 1, the biggest L is 3. And then if we do small r minus big L plus 1, that's going to be minus 1. And we can't have minus 1 cards being able to go through all of them. So therefore, it has to be the max of 0 with some number. Yeah, because the lowest number of cards that can go through all of them is none, which is 0. And yeah, and the reason we do this plus 1 is, like, let's say our big is 3 and our small is 4, right? So that means cards 3 and 4 can go through all the gates, which means there are 2 cards. So therefore it's 4 minus 3 plus 1, because that's how you count all the number of cards. And I think this should work. And voila.